Stanford University.
Well, we're going to talk about electrodynamics tonight. We've talked about scalar theories, scalar fields. We've talked about how particles couple to scalar fields, how scalar fields influence the motion of particles, in particular how the same Lagrangian, the same action, which tells the field how to influence the particle, also tells the particle how to influence the field. We're going to do that again tonight for the electromagnetic field, or at least part of it. But before we do, I really want to nail in place the notational ideas. Oh boy, what is that? Looks like quantum mechanics to me. We don't want any quantum mechanics on the blackboard tonight. Just once more, briefly, I want to go over the notations of 4 vectors, indices, how you use them, how you manipulate them. Now, just by way of philosophizing, a good notation can be extraordinarily powerful. Good notations in mathematics, the minus sign, the 0 sign, the equal sign, for goodness sakes, extremely powerful. More modern, vector notation, again, extremely powerful. What we're going to be talking about tonight a little bit is tensor notation. The trick that I showed you last time of upper indices and lower indices, that actually is due to Einstein. It's completely due to Einstein. Upper indices and lower indices, which mean nothing more than just changing the sign of the time component of a vector. A vector with upper indices and a vector with lower indices are really no different, except you change the sign of the time component. Of course, that's a special case of something much broader. It's a special case of manipulating vectors together with the metric tensor. But we're not doing the metric tensor yet. So for our purposes now, those things were just conventional conventions and notations, but notations which are quite powerful, as you will see. Let's just go over them again quickly, just to remind ourselves what those notations are all about. Oh, the other notation, which is truly brilliant, again due to Einstein, is the summation convention. But the summation convention is something that's only to be used in the right way. It's to be used when you have 2 indices which are the same, one of them upstairs and one of them downstairs. That's the only time you use the summation convention. With an upper index and a lower index, when they're the same, you can set them, or you set them equal to each other and sum over them. That's the Einstein summation convention. We'll use it all the time, but we'll only use it in the special form in which Einstein invented it. If we have summations to do and they're not of that special form, I'll write summation. Okay, so let's begin with 4 vectors again. 4 vectors have 4 components, 3 of which are space components, 1 of which is a time component. And when we're interested in the 4-dimensional geometry, we write the components A mu, but we can also remember that they consist of a time component, which is usually called A naught, and 3 space components, which are usually called A m. M goes from 1 to 3, mu goes from 0 to 3. All right, now, I've written my vector with upstairs index. I guess it's called a contravariant index. The contravariant index is the sort of thing that you would attach to dx mu. And the fact that you put it upstairs and not downstairs is purely arbitrary, but you have to put the index someplace, and Einstein chose to put the index associated with a differential displacement like this in the upstairs slot. Okay? And I guess I don't know who first called that a contravariant index, and I don't know why it's called a contravariant index, but it is. And to go from a contravariant notation to a covariant notation, this is pure definition. A mu is the covariant counterpart of A. It's the same vector. It's just another notation for it, or another way of describing it. And that is equal to eta mu nu A nu. I'll remind you what eta mu nu is. Eta mu nu is a collection of numbers. It forms a matrix, a 4 by 4 matrix, because mu and nu go from 1 to 4. And eta is just the matrix. Its components, eta 1, 1, eta 0, 1, whatever, are just the components minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. It's almost a unit matrix, and in a certain sense, with this relativistic geometry with the funny minus sign in front of time, it really does play the role of a kind of identity matrix, but it is what it is. Minus 1 in one slot, 1s in all the other slots, purely diagonal. And what this complicated formula, well, it's kind of neat. It's a nice, neat, simple setup. But really all it says is that the time component of the covariant vector is just minus the time component of the contravariant vector. That's this minus 1 over here. And all the other components are the same. All the other components are the same, so we can write then A sub naught is minus A super naught, A sub m is plus A super m, and that's all this formula means, but it's been written in a kind of neat way. Whether you find it neat or not at this point is not relevant. The point is that as you start doing things with it, you will find that you'll begin to find it very neat. All right, so let's take it for granted that it's a useful thing to do. All right, so first thing, the formation of scalars from 4 vectors. We talked about this at least twice. Let me just write it down on the blackboard. If you take 2 4 vectors, they could be the same 4 vector or 2 different 4 vectors, and you take one of them to be covariant and the other to be contravariant. Now, this thing that I've written on the blackboard automatically sums over mu. I do not have to write sum over mu here. By Einstein's convention, this means A sub 1, B super 1, naught, 1, 2, 3, and so forth. This is a scalar. In other words, this is a thing which is a quantity which doesn't change from frame to frame. Another example, incidentally, I'll just give you another example. The derivative sign, let's just put it over here for a minute. The derivative sign, d by dx mu. Now, this is a collection of 4 differential symbols, derivative symbols. Derivative with respect to x naught, which means derivative with respect to time, and the derivatives with respect to the other coordinates. It is often just written as d sub mu. Okay, another brilliant notation. Get rid of the sub x and just write d sub mu. This symbol by itself, of course, doesn't mean anything. It's got to act on something. All right? But whatever it acts on, it adds another index. If it acts on a scalar, it creates a thing with an index mu. That index, or the d by dx mu, or the d mu, is a covariant index. In other words, for example, if this were to act on a scalar field, it would give you a collection of derivatives which form a covariant vector. I won't give it a name. It's just, its name is d mu phi. All right, so the derivative symbol, yes, sir?
So it's dx sub mu, so the mu on the x is contravariant. So why is the derivative covariant?
Because it's down, because it's underneath the fraction bar. Why, indeed. All right, so last time I explained why, and I explained why if you take d phi by dx mu, and you multiply it by dx mu, what is that? That's derivative of phi with respect to time, times d time, and so forth and so on. This is just the change in phi as you go from one point to another by differential displacement dx. This is nothing but, if we call this point 2 and point 1, this is just phi of 2 minus phi of 1 divided by a little differential separation, but it is just the difference of two scalars, and therefore itself is a scalar. So, by a theorem that I didn't prove, but I told you about, if you have a contravariant vector and you multiply it by a collection of symbols with a script mu, if the result is a scalar, the theorem says that the other piece of it here is a covariant vector. So there is a theorem which says that whenever you hit anything with, or in particular a scalar, but I'll give you some more examples in a moment. If you hit a scalar with d by dx mu, it gives you a 4 vector. Everything I'm saying, incidentally, would also be true about 3 vectors. The only thing that you have to remember about 3 vectors is if we're thinking in a purely 3-dimensional language, not 4-dimensional, everything is the same except wherever you see mu's and nu's, put m's and n's, and the eta matrix is just the unit matrix. It's just the components of eta which sit in the spatial components. And for that reason, because eta is the unit matrix, there's no difference between upper and lower components. So you don't have to say, if you're talking about ordinary 3 dimensions, it's unnecessary to say whether an index is covariant or contravariant. They're both the same. Okay, another example of forming a scalar out of a vector. Well, one example of forming scalars out of vectors is just to take a mu, b mu. But another thing you can do is, let's suppose we have a vector quantity which happens to depend on position and also time, x mu. Let's not write it that way. It's a 4-vector field. It depends on space and time, and I'll just indicate that by writing x here. It depends on space-time, and therefore can be differentiated. As it stands, it's a 4-vector. It's a 4-vector at each point of space, differs from one place to another. You can also differentiate it with respect to x. And, for example, you can differentiate it with respect to x and sum over the index mu. This means derivative with respect to time of the time component of b, plus derivative with respect to x of the x component of b, and so forth and so on. This is also a scalar. All right, so that's another example of forming scalars from vectors by what we'll learn to call index contraction. Index contraction is the same as identifying an upper index with a lower index and summing. That's called index contraction. An index contraction in this kind of situation takes you from a vector, well, takes you from a quantity which has all sorts of components and leads to a scalar. Okay, now tensors, scalars and 4 vectors transform. And that's their defining property. Their defining property is the way they transform. Scalars, for example, just transform into themselves, transform under Lorentz transformations. And I'm going to give a broader definition of what I mean by a Lorentz transformation than we've used up till now. Lorentz transformations we've talked about are along the x-axis. We could have, of course, talked about a Lorentz transformation along the y-axis or the z-axis and so forth. Right? But there's another class of transformations which are also considered to be part of the collection of Lorentz transformations, and it's just rotations of space. Rotations of space is part of the collection of Lorentz transformations. Now, once you say that, then you can say that a Lorentz transformation along the y-axis is simply a rotation of the Lorentz transformation along the x-axis. You can compound rotations together with Lorentz transformations to make Lorentz transformations in any direction, rotations about any axes, and just the general set of transformations which physics is invariant under. I'm not going to show you how to do that. That's not important to us right now. The important thing is just to keep in mind that physics is to be invariant not only for Lorentz transformations along the x-axis, or the y-axis or the z-axis, but more complicated things where you rotate space, then transform, then maybe rotate back again, and there's compound rotations with, yeah.
So when you just say rotate space, then time is not affected at all?
Right. When I say rotation, I mean time not affected at all, exactly. All right? So what's a nice notation for the Lorentz transformations? Well, let's take the transformation of the contravariant vectors. For example, just x mu. How does x mu transform? X mu prime, in particular x naught prime, that's the time component, that's equal to x naught minus v x1 divided by square root of 1 minus v squared, and so forth and so on. Just the good old Lorentz transformations, except that I've called time x naught, and x I've called x1. All right. We can always write those transformations in the form of a matrix acting on the components of the vector. I'll show you what I mean. We write a mu prime, that's the components of a certain 4 vector in my frame of reference, in terms of the components in your frame of reference are given by some kind of matrix. The matrix has entries, which you'll recognize in a minute. All right. There's an upper index here. I'm going to put a lower index down here. It has 2 indices. That makes it a matrix. It has a value for every mu and every nu. It's a 4 by 4 matrix. And now it multiplies a nu. Is this a properly formed equation over here? Yeah. The left-hand side has an index mu, which can be any one of 1 to 4. The right-hand side has an index mu, an index nu, but the index nu is summed over. When an index nu is summed over, it's not an explicit variable in the equation. And so, yes, this is a properly formed equation, summation convention. All right, so let me give you an example of the matrix L just for the simplest Lorentz transformation that we've written down. I'll give you a couple of them. For the Lorentz transformation, let's say along the x-axis, let's just write down what we would put in here. We would put in here, this is the time x, y, z. Time in the first column in the first row, x, y, z. So there's a 1 over square root 1 minus v squared here. There's a minus, I think I better make this matrix a little bit bigger. Okay, let's make it bigger. In the upper corner here, we have 1 over root 1 minus v squared. And then we have minus v over root 1 minus v squared. How about the next one? Anybody want to guess? 0. 0. What about down here? minus v over square root of 1 minus v squared. And in the next place here, 1 over square root of 1 minus v squared. 0, 0. 0, 0, 0, 0. But what down here? 1 and 1. 1, 0, 0, 1. This is a standard Lorentz transformation along the x-axis. And if we write a column vector, t, x, y, z, which I could also write x0, x1, x2, x3, but let's write it this way. T, x, y, z. And we write that this is equal to t prime, x prime, y prime, z prime. Let's just see that that's correct. This is a column vector here. This is a column vector. What does it say? It says t prime is equal to 1 over blah, blah, blah times t minus v over blah, blah, blah times x. Well, that's the right transformation law for t prime. X prime is minus v over square root times t plus 1 over square root times x. That's the standard Lorentz transformation on x. And then y and z, they do not mix with t and x. Y and z, the unit matrix down here tells you that y prime is equal to y and z prime is equal to z. Good. So this is an example of a Lorentz matrix. A Lorentz matrix along the x-axis. If we wanted to transform along the y-axis, we would just shuffle these around a little bit. I'll leave it to you to figure out what our Lorentz transformation along the y-axis looks like in this matrix notation. But let's consider instead a different operation, a rotation in the yz plane in which t and x are completely left alone. This is one of these rotations which, as somebody said, don't involve t at all. Let's see what that would look like. This is a different object now, different transformation. We would put 1s here, 0, 1. That tells t and x do nothing. But what would you put down here in this lower block down here? Anybody got a suggestion? I want to rotate by angle theta in the yz plane. Now, you all know the answer. Cosine theta, sine theta, minus sine theta, cosine theta. And this would just say y prime is cosine theta times y plus sine theta times z, and z prime is minus sine theta times y plus cosine theta times z. All right, now you can take these matrices and start multiplying them and combining them to make much more complicated transformations, which, for example, are partly rotations along some axis, partly Lorentz transformations along some other axis. But this is the basic building starting point, and a formula like this. All right, so this is the transformation property of a 4-vector with contravariant index. I'm going to leave it to you to compute the transformation property of a 4-vector with a lower index. I'm going to tell you the answer, and I'll let you work it out. If you have a covariant vector, and you want to know what it looks like in my frame, given what it looks like in your frame, then there is another matrix. This matrix has to have a lower index mu, because we have to come out with a lower index here, an upper index nu, and an a sub mu. I'm going to tell you right now what the matrix M, oh, thank you, nu. If the left-hand side has a mu, the right-hand side must also have an unsummed over mu, so that's correct. Okay, now, we're talking about the same Lorentz transformation. L and M represent the same physical transformation between coordinate frames, and so M and L must be connected. There must be a connection between M and L, and it's really very simple. M is just given by eta L eta. I'll let you work that out. I'll let you prove that. Incidentally, eta is its own inverse, just like the unit matrix is its own inverse. Sorry. Eta to the minus 1 is eta. It's its own inverse, and that's because the entries here are such that they are their own inverses. The inverse of 1 is 1. The inverse of minus 1 is minus 1. All right, so you can prove this, that for a given Lorentz transformation, M and L are connected. I'm not going to use this very much. The main point is that what a 4-vector is, covariantly or contravariantly, what it stands for is an object which transforms from one frame to another in a particular and special way. And the special way is in parallel with the way the coordinates themselves transform. All right, now let's come to tensors. We're going to make heavy use of tensor notation. What is a tensor? A tensor is simply a thing with more indices. Actually, a scalar and a vector are special cases of tensors. A scalar would be called a tensor of rank 0, which means it has no index. A vector is a tensor of rank 1. And a tensor of rank 2 would be a thing with 2 indices. So let me give you the simplest example of a tensor. Take 2 vectors. In fact, it would be enough to have 1 vector, but let's take 2 vectors, A and B. Now we can make a product of A and B by, and that's a scalar. But now I want to consider a more general kind of product. The more general kind of product has 2 indices, mu and nu. Let's begin with the contravariant version of it. Let's just put it next to each other, A mu and B nu. Now, this is an object. How many components does this thing have? 16. 4 times 4. There's A naught, B naught, A naught, B1, A naught, B2, A naught, B3, A1, B naught, and so forth and so on. There are 16. This is a symbol here stands for a complex of 16 different objects, different numbers. Okay? It's just the set of numbers you get by multiplying any component of A with any component of B. It's got 2 indices, and it's called a tensor. I'm going to label it just generically. I'm going to write T for tensor, and it's a particular tensor T mu nu. Not all tensors are of this form. Not all tensors are simply constructed out of 2 vectors this way. All right? But 2 vectors define a tensor in that way. How does such an object transform? How does this object transform, T mu nu? Well, if we know how A transforms, and we know how B transforms, which is the same way, we can immediately figure out what, let's call it A prime, put a bracket around here, mu B prime nu is. All we have to do is transform the A and the B, but we know how the A and the B transform. Let's rewrite this using the transformation here. I'll tell you what, I'm going to change the symbol here. Instead of calling this nu, mu nu sigma. Remember, it doesn't matter what you call a summation index as long as you're consistent. You're summing over it, and so it's just a thing that is a sort of dummy index. Okay, and let's do it here also. Mu sigma, sigma. Let's plug in here. This is just equal to L mu sigma, put it over here, A sigma. But now we also have to put B prime, and B prime is the same sort of thing, L nu, and let's call it tau, A tau. L mu sigma times A sigma, that's A prime. L times this A, sorry, excuse me, B sigma. B sigma. B prime mu sigma sigma. Right? Good. Tau, tau. Good. Now we're cooking. Sigma goes with A, tau goes with B, and now the equation is consistent. So here we have a new rule about a new kind of object with two indices, which tells us how it transforms. It transforms with the action of the Lorentz matrix on each one of the indices. So now we can abstract from that and say more generally, the way a tensor transforms, let's call it the tensor, the primed tensor, the quantity, the set of quantities that I see are related to the set of quantities that you see by L mu sigma, L nu tau, times T sigma tau. A times B, that's T sigma tau. So this is the rule, for example, for the transformation property of a simple tensor with two indices. Tensors can have, yeah.
Wouldn't this be predicated on the idea that the L's, the A's, and the B's can commute? Because it would be L, the L and the A go together, and then the L sigma and the A.
We're not doing quantum mechanics, so everything commutes.
Okay.
And there's only one matrix here, L. Every matrix commutes with itself. So there's no issue of commutation here. Okay. You can invent more complicated kinds of tensors. Tensors with three indices, mu, nu, I don't know, lambda. How would this transform? And you can think of it by just thinking of it as the product of three vectors with index mu, nu, and lambda. I won't write it down, but the way that it transforms is straightforward. For each index, it's a transformer for each index. Nu tau, and now we need one more, L lambda kappa. T sigma tau kappa. That would be the general transformation property. And of course, you generalize the hell out of this, any number of indices, and that's the way, that's basically the definition of a tensor. The definition of a tensor is a thing which transforms like this. Now, as I said, not every tensor is formed from the product of two vectors. For example, supposing there were two other vectors. Suppose there were two other vectors, C and D. We could take B mu, A mu, B nu, and add it to C mu, D nu. Adding tensors, by assumption now, adding tensors gives other tensors. So if I take the tensor A times B with mu index and nu index and add to it C times D, that's something which cannot be in general written as the product of two vectors, but it's a tensor. It's defined by its transformation properties, not by the fact that it may or may not be associated with just a pair of vectors. Okay, so now we know what a tensor is from its transformation properties.
How exactly does multiplying a matrix by a tensor work?
Well, how does, it works exactly this way. This is sorry, this way right here. Here's a matrix L, and it acts on T. Write out what this means in detail. There's a lot of components, but I'll give you a hint. For example, T 3 1 prime. Okay, what is that? That's equal to L, now this is 3 sigma, L 1 tau, T sigma tau. And now you start going through it. Yeah, sigma could be 0, tau could be 0. There's 16 possibilities. 0, 0, you mate that with T0, 0. So one term would be L3, 0, L1, 0, T0, 0. Then there would be another term, L3, 0, L1, 1, T0, 1. And so forth and so on. There would be 16 such terms, one for each index here and in each index here, and you add them up. All right. So that's the idea of the transformation property of a tensor. And the thing about tensors, vectors, scalars, tensors, the thing about tensors is if they are equal in one frame, they are equal in every frame. That's easy to prove. But to say that they're equal means all components equal. If all components of a tensor are equal to all the components of some other tensor, of course then they're the same tensor, but or another way of saying it is if all the components of a tensor are 0, shift everything to the left side. If all the components of a tensor are 0, they are 0 in every reference frame. Okay, so to say that a tensor is 0 is an invariant statement. As I said, it's not enough to look at some component and say that component is 0, the whole thing is a tensor, so it must be 0 in every frame. No. If all the components are 0, there's 0 in every frame. And that's the power of tensors. It allows you to make statements and allows you to write down equations which, if they're true in one frame, will be true in another frame after transformation. That's the basic power of it. All right, now I've told you how to transform a tensor with all of its indices upstairs. I could start writing down the rules for tensors with some indices upstairs, some indices downstairs, but I think I won't, and instead I will just tell you that once you know how a tensor transforms, you can immediately deduce how its other variants transform. The other variants, for example, the other versions of the same tensor, same geometric quantity, but with some indices upstairs and downstairs. For example, A mu B nu. That would be some tensor with one index upstairs and one index downstairs. How does it transform? Never mind, you don't need to worry about it, because I will tell you immediately that this tensor here is given by T mu sigma, which you understand and know about how to transform it, times eta nu sigma. To lower an index, to take a tensor, and to take an index from contravariant to covariant, you multiply. You do it exactly the same way that you do it for a vector. You take that index and you lower it by the operation of eta. So, again, this is a well-formed equation, or well-formed symbol. Sigma is summed over. And this here object is T mu nu. All right, but there's another way to think about it, an easy way to think about it. Given a tensor with all of its indices upstairs, what do you do to pull some of the indices downstairs? And the answer is very simple. If the index that you're pulling downstairs is a time index, you multiply by -1. If it's a space index, you don't multiply at all. That's what eta does. So, for example, here's the tensor T naught naught, which is exactly the same as t naught naught, because I've lowered two indices. Lowering two indices is two minus signs. Okay? It's like the relation between a naught b naught and a sub naught b sub naught. There are two minus signs in going from a super naught to a sub naught, and going from b super naught to b sub naught. Each one has a minus sign. This is equal to this. But what about this one? A naught b1, and how does that compare with a naught b1? Sorry, a naught b, let's put one down. Let's put both of them downstairs. B super 1 and B sub 1 are the same. But A super naught and A sub naught differ by a minus sign. So T naught 1 would be minus T naught 1 because only one time component was lowered. Every time you lower or raise a time component, you get a minus sign. And that's all there is to it. But having a neat matrix notation is a fast summary of that fact, that the relation between covariant and contravariant is just every time a time index goes from upstairs to downstairs, it's a minus sign.
Question.
Yeah.
Why is it useful to have these two forms, contravariant and covariant?
Just so you can write things like that. How else would we write A naught B naught minus A1 B1 minus A2 B2? That's it. Sorry, not this one, but yeah. This complicated thing, which requires four terms, let's put the minus sign here, plus, plus. One minus sign, three plus signs, and four terms altogether is just.
So you can do products of the signs working. Is that
Yeah, that's all. That's the reason.
There's got to be more to it than that.
There is.
You need it in display R.
There is more, but the more to it is best described when we go to general relativity. For us right now, it's just a neat tool for manipulating indices. It's a neat tool for manipulating indices and minimizing the number of indices we need.
When you asked earlier how many terms in AU, BU, I said UU, and you said 16.
That's 16 in A mu, yeah, in A mu B nu, there are 16.
So are tensors always 4, or is it just in the context of relativity we're dealing with?
Right, that's, yeah. In the context of relativity, because there are 4 coordinates, the indices run over 4.
So this would
Right.
in general work for any indices, but in our class,
Yeah.
this is 4.
Yeah, yeah, but I mean, no, it's worthwhile keeping in mind that, that it would work. Yeah, that's right. That's correct. And in fact, the analogous version of it for three-dimensional space is essentially the same, but slightly simpler in that you don't ever have to distinguish upper and lower indices. That's it. Okay.
Can you give a more general description of the covariant and contravariant?
I certainly can, but not tonight. Okay. Right. Right. It has a geometric significance, but you know, the geometric significance is something everybody figures out for themselves and then promptly forgets because you never really think about it. You just learn to manipulate the indices, and it's so quick and so efficient and so fast that. But yes, it does have it does have a geometric meaning. The geometric meaning is. Well, okay, I don't want to get into it now. I wanted to. Tonight's lecture is really about electrodynamics, and we ain't going to get there. All right. Now, let's talk about the different kinds of tensors. Now, I'm talking about tensors with two indices. Let's talk about two indices. Here's a tensor with two indices. Now, this is not necessarily the same, and in fact, it is not the same in general as t nu mu. Changing the order of the indices in general counts. For example, a mu b nu is not the same in general as a nu b mu. This could be a naught b1, and that's not the same as a1 b naught. Just not the same. All right? So in general, tensors are not invariant under changing from on changing the order of the indices. Okay? But there is a special case called symmetric tensors. Symmetric tensors are ones which do have this property that t mu nu is equal to t nu mu. Let me construct one for you. A mu b nu plus a nu b mu. If you interchange mu and nu, this doesn't change. What happens is this becomes this, and this becomes this, and it's the same quantity. So you can construct out of any tensor a symmetric tensor by adding together some tensors are symmetric, others aren't. Okay? Some tensors are symmetric, others aren't. A symmetric tensor has a special place in general relativity, not so important in special relativity. Well, it'll come up. But more important for us tonight is the antisymmetric tensor. Let's call it F mu nu. The tensor which, when you interchange nu and mu, changes sign. We could construct such a tensor by putting a minus sign here. Putting a minus sign there would construct a tensor which would change sign when you interchange mu and nu. If you interchange mu and nu, this gets swapped with this, but there's a minus sign. So there are symmetric tensors and antisymmetric tensors. Antisymmetric tensors have fewer components than symmetric tensors. And the reason is their diagonal components vanish. For example, one of the things this equation says is that f naught naught is equal to minus f naught naught. Set mu and nu equal to time. F naught naught is minus f naught naught. The only solution to that is 0. So if you think of a tensor as an array, a matrix if you like, if you think of it as an array, then an antisymmetric tensor, this is the one we're going to be interested in, is completely 0 on the diagonal. And the off-diagonal elements, I'm going to give them names now. I'm going to give them names. I'm going to call this one minus e sub 1, this one minus e sub 2, and this one minus e sub 3. And these names are, of course, chosen for future purposes, but I'm just going to write them down now. And they're just labels for now. Minus B3, B2, and minus B1. Now, what do I put down here? I haven't written all the elements of it. But I'm assuming that this F tensor is antisymmetric. If it's antisymmetric, it means that as a matrix it's antisymmetric. It means down here we put plus E1, plus E2, plus E3. Let's see, there's an element down here which must be plus B3, minus B2, and plus B1. It's antisymmetric, which means you just flip the sign when you reflect it around the diagonal. That's the notion of an antisymmetric tensor, and it plays a key role in electromagnetism, where E's stand, of course, for electric field and B stand for magnetic field. The electric and magnetic field, as we will see, we're not there yet, but as we'll see, the electric and magnetic field combine together to form an antisymmetric tensor in relativity. The electric and magnetic field are not two independent things, and in particular what that means is that when a Lorentz transformation is performed, the electric field can become magnetic field, just like X can get mixed with T, E can get mixed with B. So what you see as a pure electric field, I might see as having some magnetic component to it. All right, but we're not there yet. That was just by way of notation, strictly notation. All right. Let's now begin with the physics part of tonight's lecture. This was all notation and abstract, rather dry. Well, we'd all go crazy if I had to write 0, 0, 1, 1, 2, 2, 3, 3 every time I wrote an equation. And so it's good to have this notation. OK. Now, we could begin either studying the dynamics of the electric and magnetic field, or we could begin by studying the motion of a particle in an electric and magnetic field. The dynamics of the electromagnetic field would be the equations of motion that electromagnetic fields satisfy. The Maxwell equations, to put it briefly. Whereas the equations of a particle moving in an electromagnetic field are the Lorentz force law. Let me remind you what the Lorentz force law is, and then we're going to derive it from something else. We're going to derive it from a combination of relativistic ideas and the action principle. All right, I'll just remind you, mass times acceleration. This is a low velocity version of it. Mass times acceleration, where we don't have to worry about relativity too much. Mass times acceleration is equal. Now, on the right-hand side, you have the electric charge of a charged particle times the electric field. Mass times acceleration is electric field times electric charge, and the other term is the magnetic charge, the magnetic force, which also involves an electric charge, plus, I think it is, velocity of the particle cross product with the magnetic field. All right. Cross product, I assume you know how to think about cross products. We'll use them over and over again. I actually have a little section in here on cross products, but I'm not going to do it tonight because I think we've done it enough times. There are some speeds of light in there. I'm going to set them all equal to 1. This is usually taken to be V over C, V divided by C. I think that's the only speed of light in that formula. Little e is just the electric charge measured in appropriate units, measured in the appropriate units. All right, that's the non-relativistic version of the Lorentz force law, of which we're going to derive the relativistic version tonight, and the full-blown relativity. And we're going to find that these two terms are really part of the same term. They're really part of the same thing, written in a way where all reference frames will get the same answer. All right, so to ensure that, that our answers respect the rule that the law of motion of a charged particle is the same in every reference frame, we want to write an action principle where the action is invariant under Lorentz transformation. That's the key. Action invariant under Lorentz transformation. For a single particle, we had a formula. Let's go back. I don't need this now. We'll come back to it. For a particle without any field, we just wrote down an action which was the integral along the trajectory from 1 to 2, 1 and 2 being the starting point and the end point of the trajectory, minus the mass times the proper time interval. Proper time from one point to the next, minus the mass times the total proper time from 1 to 2. And we rewrote that as the square root of 1 minus x dot squared, where x dot, let's remember what x dot squared is. X dot m is the mth component of velocity. Here m is just a 3-vector symbol. xm dot and x dot squared means x1 dot squared plus x2 dot squared plus x3 dot squared, and so forth. In other words, the total square of the velocity. That's what x dot squared means here, summed over 1, 2, and 3. All right, so that was the action integral dt. And that identifies minus m times the square root as the Lagrangian of the particle. We worked that out. We found out what the momenta were, what the energy was, and we'll just leave that. What do we add in an electromagnetic field? Well, I haven't told you much about electromagnetic fields yet, but the basic structure which enters an electromagnetic field is a 4-vector. A 4-vector, the electric and magnetic fields themselves are derived quantities. The basic underlying quantity is a 4-vector A mu. And it's a function of position. And time. It's the field describing electromagnetic waves, if you like, or electromagnetic fields in general, and it's a 4-vector. The electric and magnetic fields are derived things which we're going to derive. I think we're going to derive them tonight. I'm going to try to derive them tonight. But the basic starting point is a 4-vector. The 4-vector is called the vector potential, or the 4-component vector potential. And we'll learn what it has to do with electric and magnetic fields in a moment. But what do you do with it to construct an action for the particle in the electromagnetic field? And the answer is very simple. It's in many respects simpler than the thing that we did with the scalar field. A mu is a field with a lower index. The natural thing to do with it along a trajectory is to take a little segment of the trajectory described by dx mu, a little 4-vector from here to here. And what can you do with such a 4-vector if you have another 4-vector, in particular a 4-vector with covariant indices, to make a little scalar quantity associated with that little gap there? Well, you take the two vectors and you multiply them together with one upper index and one lower index. I'll write in here that A mu is a function of x, which means x and t. And then you sum them all up. You integrate from one end to the other, from 1 to 2. And this is just another way of saying for each little gap there, take the differential distance along that segment and multiply it by A mu to form a scalar. The x mu times A mu is a scalar. Everybody agrees about its value on each one of these little segments, and we add them together. You can add them as well as I can add them, and we will get the same answer for the action because what I wrote here was a scalar. I added them all up, adding quantities that we agree about. We'll continue to agree about them. What more can I do with this? Not much. The only other thing that I'm going to do to it is I'm going to multiply it by a constant, and we're going to call that constant E. It is the electric charge. And because of a notation that was first put in place by Benjamin Franklin, there's a minus sign here. That's arbitrary. It depends on our definition of electric charge. And had the proton been, well, and, yeah, okay, so there's a minus sign. So here's the other term in the action of a particle moving in an electromagnetic field. Let's write it up here. Minus E times an integral from the same point from 1 to 2 dx mu a mu of x. Now what do we want to do? We want to write down Lagrange's equations. We want to write down Lagrange's equations for the motion of the particle. And really my goal is to write Lagrange's equations and show that they're just the Lorentz force law. But I would like to do it in a way which is relativistically invariant. MA, mass times acceleration, is a very non-relativistic formula. What, for example, is relativistic acceleration? What does acceleration mean? Does it mean the second time derivative of the position with respect to time? Or does it mean the second time derivative of any one of the 4 coordinates with respect to time? Or does it mean the second time derivative with respect to proper time? Well, I think we probably can guess that the invariant, or the best definition of acceleration in relativity, is to differentiate the coordinates twice with respect to proper time along the trajectory. Right? That's a guess. Right? It is the right definition, and in that form, acceleration is a 4-vector. We want to write 4-vector equations, but we're going to begin with a thinking about velocity being derivative with respect to time, and later when we calculate the equation, we'll go back and make it Lorentz invariant. Now, we won't change it. We'll rewrite it in a way which you'll recognize as an equation among 4 vectors. Okay, so let's leave it this way for the moment. This quantity in here would be the Lagrangian. So this would be the Lagrangian for the free particle. But there's another contribution to the action over here. So let's write this in a form which would make it look like a Lagrangian. This is very easy. We just divide by dt and multiply by dt. All right, so let's see what we have here. There's dx naught by dt. What is dx naught by dt? X naught is t. So dx naught by dt is just 1. And the first thing we get here is a naught dt. And a naught is a function of x and t. So that's the first term. dt by dt, that's trivial. Now the next term is minus e integral. Let's call this one now x. So it's dx by dt, which is x dot, times a sub x dt. And likewise for y and z. And so the rest of this is simply xm dot am, or xm dot. The mth component of velocity dotted into dot product, mth component of velocity dotted with the mth component of the vector potential. That's what this is. And the reason I wrote it this way with the dt here is to make it have the familiar look of a Lagrangian action, an action written as an integral over dt. Okay, so let's write it down now. Minus e integral a naught plus xm dot am dt. And now we can identify the Lagrangian. Let's calculate it's here. The Lagrangian is here. It's just everything inside the integral here. The Lagrangian for this system, for this particle in an electromagnetic field, is just minus m square root of 1 minus x dot squared, which means x dot squared plus y dot squared plus z dot squared, minus electric charge A naught, that's this one, minus electric charge x dot m, am of x and t. The a's are just functions of x and t. They're fields. Just like we did with the scalar field, I'm going to imagine that somebody told us what a of x and t is. Somebody told us it's just a known function. Each one is a known function of x and t. And now we're just exploring the motion of the particle in that known field. And here's the action for it. What do we want to do with it? We want to write the Euler-Lagrange equations. And we want to show that they look like the Lorentz force law. Okay, so that's our goal. Take this Lagrangian and see if we can derive the Lorentz force law. Mass times acceleration is equal to electric field plus, electric and magnetic Lorentz forces. All right, so where do we begin? Let's consider the equation of motion for xm. So we start with partial of L with respect to xm dot. That's the starting point. All right. There's obviously a contribution from the first term here, and we've already done with that. We know what that is. It's m. Incidentally, this m is not the same as this m. This m is an index. This m is a mass. Okay, let's not get confused. I apologize for that, but it's too late to do anything about it now. This one is mass. This one is the component m. M times xm dot divided by square root of 1 minus x dot squared. That's the derivative of this Lagrangian here with respect to the mth component of velocity. That's easy. Another, we've done that before. Incidentally, this happens to be m times dxm by d tau. It's the x by dt, but this extra factor here just makes it the 4 velocity, the 4 vector of velocity. This is m times the 4 vector of velocity, the xm by d tau. But we'll come back to that. For the moment, let's just leave it this way. And then what do we do with that? We take the derivative with respect to time. So we get m d by d time xm dot divided by square root of 1 minus x dot squared. That's the left hand, well, sorry, that's one term. Oh, sorry, this is not right, is it? No. Why isn't it right? Yeah, there's more stuff there. There's more stuff there, right over here. Let's put it back in. What is it? It's minus e times a sub m. From here, derivative of the Lagrangian with respect to x dot gives us another term, which is just the vector potential. Electric charge times the vector potential. And so what we have to do is be careful, first of all. This is m times this minus e a m. That's the left-hand side. That's the full left-hand side of the Euler-Lagrange equation. How about the right-hand side? The right-hand side should just be dl by dxm, right?
Did we switch between co and contra x's?
Yes, I did. But remember that this, we can put it back. Yeah, I did. But remember that when you switch the space components, it doesn't matter.
Does that require an A, switch in the A?
It doesn't matter for A either. Right. All three-dimensional components, it doesn't matter. Right.
Question, are we summing on Latin indices?
Only sum over repeated indices. And don't count the mass as an index.
But, I mean, Latin and Greek doesn't matter?
Well, let's see, where might have I done that? Yes, over here I did. Yeah, over here I did, and so, right. With Latin indices, it doesn't matter whether they're upstairs or downstairs, and if they're repeated, you sum over them. But you only sum from 1 to 3, not from 0 to 3. Okay? So that's, yes, that's part of the notational trick. All right, so here we have the left-hand side of the Euler-Lagrange equation. And what do we have on the right-hand side? On the right-hand side, we have the derivative of the Lagrangian with respect to xm. All right, so where does it depend on xm? A naught depends on x. It's just thought of now as a fixed known function of the positions of the particles. And so on the right-hand side, we will have minus e times the derivative of a naught with respect to xm. Now, does that look familiar in any way? On the left-hand side, something that's sort of like mass times acceleration, and on the right-hand side, something which is minus the derivative of something. This is clearly, E times A naught is clearly the electrostatic, is the potential energy. Is the thing which in mechanics we would ordinarily call V or U or whatever we call potential energy. So this here is just familiar. It's here, left-hand side here has something like mass times acceleration. If we didn't have this thing downstairs here, which is, after all, is very close to 1 for slow motion. If the motion is slow, this literally is mass times acceleration. This term we'll worry about later. And on the right-hand side, we just have minus the electric charge times the derivative of the electrostatic potential. Okay? So this is potential energy over here, or the gradient of potential energy, which is essentially electric field. But we'll come back to that. All right, but now there's more. These terms also depend on x, and I have to differentiate them with respect to x. These terms are mixed. They depend on both velocity and position. We've already taken into account the fact that they depend on velocity. That was on the left side of the equation. On the right-hand side of the equation, we have to write minus e. Let's call this here n. It's a summation index. xn dot times the derivative of an with respect to xm. Now where did all this come from? It doesn't matter whether I call this n or m, it's summed over. But by the time I got down to here, the m index was not summed over. So I don't want to call the summation index m. I called it n. I switched it. All right, why am I differentiating with respect to xm? Because the right-hand side of the Euler-Lagrange equation is the derivative of the Lagrangian with respect to xm. So we have xn dot derivative of an with respect to xm. So look at this. Look at it carefully. The left-hand side has an index m, which is unsummed over. The right-hand side has an index m, which is unsummed over, not summed over, but it also has an index n, which is summed over. This is the Euler-Lagrange equation for each component of the position, x1, x2, x3, and so forth. It doesn't look like anything you might recognize yet, let's see, and unfortunately, there's no simple way to deal with it except to deal with it. So let's, okay. This side over here, that's easy. That's just, we're not going to change that. D by dt of m, take m on the outside, x dot m, or m, doesn't matter, upper or lower, it doesn't matter, over square root of 1 minus x dot squared. All right, that's this term over here. Now, how do we differentiate this thing with respect to time? This doesn't, it may depend explicitly on time, but even if it didn't depend explicitly on time, it still wouldn't be constant. Why? Because the position of the particle is not constant. The position of the particle is moving, and so even if m only depended on position and not on time, a sub m, as it tracks the particle, as it follows the particle, would depend on time. So there are two terms when you differentiate a sub m. Let's see what they are. There's minus e, and the first term is just the explicit derivative of am with respect to t, am of x and t. But then there's another term, and the other term is minus e times the change in a when x changes. Now let's see, xn, am, xn dot. Now, if you haven't gone to sleep yet, let's just see what we have. We have the time derivative of a. It's over here. A depends on time explicitly if the field is changing with time, but it also depends on time implicitly from the fact that the position of the particle is varying with respect to time. All right, so we differentiate a with respect to position and multiply by velocity. This is a dummy index. It's summed over. This one is the index that appears on the left side of the equation. So what do we have? That's this side of the equation. And on the right-hand side, we're still not finished. We still have the right-hand side, a bit of a mess, minus e times the a naught by dxm. That's this term. That's the potential energy. And then there's this term over here, minus e xn dot dan by dxm. It's a lot of stuff. It's more stuff than I usually like to do on the blackboard, but no way around it. So let's take this and call this ma, mass times acceleration. It's not literally acceleration, but let's just call it, let's think of it as mass times acceleration. Leave it on the left-hand side, m d by dt x dot m over square root, and put everything else on the right-hand side, and then group things together. We're going to group them together into two kinds of terms. One kind of term is not proportional to a velocity. This has no velocity multiplying it. And here is another term which has no velocity multiplying it. The second term here on the left-hand side has a velocity, and the last term on the right-hand side has a velocity. So we're going to group things by whether they have a velocity or don't have a velocity. Now, just remember where we're going. We're going to electric field times electric charge, which does not have a velocity, and then v cross b, which does have a velocity. That's where we're going. And we're trying to identify now those two terms. All right, so left-hand side is, let's just call it mass times acceleration, but put some quotes around it to indicate that it's not the literal second time derivative of x with respect to t, just left-hand side. On the right-hand side now, we have the two terms which don't involve time, velocities. We have e times dAm by dx naught, the am by dx naught, I've now reverted to calling time x naught, minus, same e, dA naught by dxm. Notice the nice symmetry here. It has dAm by dx naught, and it has dA naught by dxm with a minus sign. Obviously, this thing wants to be electric field. It has no velocity in this term over here. So if there's any sense to all of this, this must mean mass times acceleration is electric charge times electric field. And indeed, it is the electric field. The electric field has two terms. One of them is the gradient of the time component, and the other term is the time derivative of the space component. All right, so that's one thing. We will later see that this falls nicely into place as electric field. Now, what about the terms involving velocity? Let's get them. We bring this one over on the right-hand side, so it's plus E. We have both of them have xn dot. So let's put xn dot out here. And one of them has, let's see, where is it? Bracket. One has dAm by dxn, and the other one has dAn by dxm. Notice the pattern. Each term here, oh, yeah. Right. The pattern, apart from the x dot, is each of these terms has a derivative of an a with respect to a coordinate anti-symmetrized. Notice that anti-symmetry there, that it's am by x naught minus a naught by xm. am by xn minus an by xm. Interchange of n and m over here, and interchange of m and naught over here. All right. Let me do something over here to make this term a little more parallel to this term. I'm going to write something stupid here. I'm going to write t dot here. What on earth is t dot? It's dt by dt. It's just one, huh? Yeah. All right. Or I could also write it as x naught dot. It didn't do anything. It just I just threw in for free dt by dt, which is just 1. But now it starts to look kind of symmetric with respect to space and time a little bit. Here we have a anti-symmetrized thing with an index m and n, and here we have an anti-symmetrized thing with naught and m. This is xm dot here. Sorry, yeah, that's right. I got it right. It's right. Okay, so this is the form of the equation of motion. This is electric field. This, of course, is the magnetic field. This is the magnetic field. To identify in detail how the components of magnetic field, what is this operation over here? What mathematical operation have I done on the components of the vector potential? The curl, right? It's the mathematical curl, but we'll come to it. I didn't want to do that tonight. These are the components of the curl of A, and the curl of A is the magnetic field. This here contains one term, which is just the gradient of the time component plus another term, and this constitutes the electric field. All right. Good. All right, everybody happy with this? It's a bit much, but I tell you now, go through this. This is something, you know, if you really care about this, here's your Lagrangian. Where is it? This is, sorry. Top board. There's your Lagrangian. Go through the Euler-Lagrange equations, collect together the terms. One side you'll call MA. The other terms have terms with velocities and terms without velocity. This, of course, didn't have a velocity. It was just one. And group them together and show that this is the way they group together. You will learn a lot, both about field theory, about a little bit of calculus, and especially about electrodynamics. Okay? Yeah.
At the very beginning, for the electromagnetic part of the action integral,
This is, of course, just the action on the particle, of the particle motion, right? Yeah.
why did you write that the integral of A over, well, you had a four-vector form, but the thing on the right, you have there now.
This,
That's the,
this integral is minus E times the integral of A mu dx mu.
so, but why did you write that? That's really my question.
There's hundreds of years of experiment. But what constrains it? I think the right answer is not why did I write down exactly this. That's partly experiment. Okay? But what is it that this integral has? What properties does it have which make it a good candidate? First of all, the action is an integral along the trajectory. That's a rule that up till now we've respected, that the action is to be thought of as little incremental pieces. So it's a bunch of incremental pieces. And the other rule is simply that it should be a scalar, that it should be composed out of scalars. Given a dx mu, there are basically two things you can do with it to make a scalar. One is to multiply it by itself. And what is that? That's just d tau squared. That's already in the Lagrangian. Here is d tau is just the square root of that. That's in the Lagrangian already. It doesn't involve any field. What's the other thing you can do? You can dot the four-vector of velocity. You can dot the dx, or not dot, but you can multiply dx by a and contract the indices. If you can find another way to make a scalar, you're welcome to play with it. Okay, and there are other ways. There are other ways. We have not got yet to the concept of gauge invariance. But I prefer to work with it at this level first, and then to study its gauge invariance after we've gone this far. So this is basically the simplest thing we could have written down. You could write down, you could multiply it by a nu. You can take a scalar and multiply it by another scalar. You can write down a lot of junk. All right? But this is very much the simplest, so let's explore it. Let's do it in that frame of mind, an exploration of a simple action. What happens? You start grinding it out. You get a set of equations of motion, which are the Lorentz force law. Okay.
You know you made the right choice. Once that comes out of the
Yeah, you know you've made the right choice, right? Right, but we haven't used all the principles yet. We haven't identified all the principles yet.
Can you derive Maxwell's equations from the principle of least action?
Oh yes, we're going to do it. Oh, we will do exactly that. But we will need another term in the action. The other term in the action will be the field part of the action. Not the particle moving in the field, but just the part of the action that governs the field by itself. All right, that's what we did for the scalar last time. Okay, so let's keep going.
In that, the last equation there,
This one? Yeah.
Can you just show again explicitly where the summations are occurring by the notation?
Okay, there's no summation here. This is the mth component of the acceleration. That's it. It's the mth component of the acceleration. And there's no summation over here. There's just an m index, and that's all. There's an n index over here that is combined together with an n index over here. There's a repeated index, xn, d by dxn times xn dot, and dan times xn dot. N is the summation index, so literally this is sum over n, if we wanted to put the summation sign, sum over n. But the rule is repeated indices get summed over. Non-repeated indices are explicit, and they're on both the left-hand side and the right-hand side. Let's see if we can write this formula in a way which is manifestly, that means obviously, Lorentz invariant. At the moment it is not, and the reason is that the left-hand side and the right-hand side are not themselves 4 vectors. They're not 4 vectors, but we can convert them to 4 vectors. So let's do that. Yeah.
Could you say something about why that term is the electric field, the partial of AM with respect to x naught minus the partial of AL with respect to xn?
Well, all right, what would we write if it was electric? What do we want to write? We want to write E.
Sort of by definition?
Yes. We want to write E times the mth component of the electric field. What's special about this is it doesn't involve a velocity. It just depends on an electric field which depends on space and time. But this term does not contain a velocity, and it's not a velocity-dependent force. All right. Force doesn't depend on velocity, it only depends on where the particle is. And so here we have a term which is like that. Over here, we have all the terms which multiply velocity. And so it better be that that corresponds to the magnetic field. But I think what you're saying is right. I mean, if we started from this principle, if we started from the principle of least action, and we wrote down that action, and we eventually got this equation, we might look at it and say, let's take this whole thing here. It doesn't matter whether it's part this and part that. Let's just call that E. And we would have invented or discovered the electric field. So I think that in fact really is the natural logic. Natural logic is to identify this and call it the electric field. And in a like manner, we will identify this with components of the magnetic field. V times something. Okay, but not yet because I don't want to do that yet. All right, let's see if we can write this in a form, first of all, which is obviously Lorentz invariant. Obviously invariant means that you should write it as the left-hand side and the right-hand side being tensors of the same kind. Well, this obviously wants to be a vector type thing. It doesn't want to be, it has a component. The component is a spatial component. It sounds like it's part of some kind of 4 complex which you might identify as a 4 vector, but not quite. And let's see what we can do with it. Okay, so what was it really? What it really was m times d by dt of the x mu by xm by dt, or xm dot, divided by square root of 1 minus, let's just call it v squared. I called it x dot squared before. This quantity, x dot over square root of 1 minus v squared, x dot means dx by dt. This is dx by dt. This happens to be exactly dxm by d tau. Do you remember what we call that variable, that quantity, the xm by d tau? We called it the 4 velocity, and there was a letter that I identified with it. U. Of course, there's also a fourth component. There is a fourth component. The fourth component would be dx naught by d tau. That would be u naught. For slow particles, this is very close to 1, but nevertheless, it's there. But at the moment, what we have here is literally d by dt of dxm by d tau. In other words, the time derivative of the 4 velocity. Okay, and that's equal to the right-hand side. The right-hand side will also manipulate in a little while. But I don't want to have a d by dt here. I want to have a d by d tau there. Why do I want a d by d tau? Because tau is the invariant quantity. I don't want to have I don't want to have this kind of mixed thing with a tau and a t. D by d tau, that's Lorentz invariant. Tau doesn't change from one frame to another. But t does. So what do I do with this? I'm going to multiply whatever's here, all the stuff here, all the stuff that comes from the right-hand side of the equation, wherever it is. I'm going to multiply both sides of the equation by dt by d tau. dt d tau. What do I get on the left side? d by dt, dt d tau, what's that? That's just d by d tau. dt's cancel, and this is just the rate of change with respect to tau. That's after I multiply by d by dt. And this is a nice expression. This is just a mass times a second derivative of the component with respect to tau squared. This is part of a 4-vector. If I add the first 3 components, x, y, and z, if I add to that a 4th component, which is the second derivative of time with respect to tau squared, that is a 4-vector. It's the 4-vector m d second x mu with respect to tau squared. It's a kind of acceleration, but it's an acceleration just as the Lorentz invariant concept of a velocity is to differentiate the 4 components with respect to the proper time. The Lorentz invariant notation, the Lorentz invariant concept of an acceleration is to take the second derivative of all 4 components of position with respect to the proper time. So we can do that on the left side. All right, that gives us what is standardly called the proper acceleration. That's called the proper acceleration on the left side. For slow-moving particles, it's close to the ordinary acceleration. All right, let's look what's on the right-hand side. Let's go to the right-hand side here, and now multiply it by dt d tau. All right, let's multiply it by dt d tau. So we have here it's dx naught by dt d tau is the same thing as dx naught by d tau. Let's multiply it. We're multiplying. Dx naught by d tau. But what's over here? This is dxm by dt. Now I'm multiplying by dt by d tau. So what does that make that term? It just makes it dxm by d tau. Now look at these 2 terms. They have exactly the same form. The same form, but with a different index. Here the index is 0, 0. Here the index is m and n. This can all be summarized into a single equation, or a single term, and the single term is E times the A m by dx mu minus the A mu by dxm times dx mu by d tau. On the left-hand side, on the left-hand side, it's d second by d tau squared m of xm equals. This is xm, not mu. Wouldn't it be nice if I could change this m to a mu? This is an equation, this is 3 equations for the space components of the proper acceleration. On the right-hand side, we still have space components here. Wouldn't it be nice if there was a 4th equation? This is 3 equations, 1 for each m, 1, 2, and 3. Wouldn't it be nice if there was a 4th equation, which was just the time component of this? Same equation, except with m being the time component over here and the time component over here. If that 4th equation was correct, then we could summarize the entire set of equations by basically one equation: mass, proper acceleration, all 4 components, dx mu, equals E times the derivative of A mu. What do I have here? A mu with respect to x nu minus derivative of A nu with respect to x mu dx mu by d tau. No, dx nu by d tau. I think I should have x in here. N in. All right. Let me write that equation down again. Your homework is to go home and derive the following equations. Oh, do I know that the 4th equation? Let's just rewrite it. Here it is. This is a complex of 4 equations, 1 for each mu. 1, 2, 3, and 4. The first 3 of them, or the last 3 of them, 1, 2, and 3, are just the equations that were written here when m is 1, 2, and 3. I've added an equation. The equation I've added is for the second time derivative of x naught. How do I know that it's true? Why should it be true?
Because the first time derivative would be constant, the second time would be 0.
Whoa. No.
Proper.
No. The left-hand side is literally a 4-vector. So is the right-hand side. This is a tensor. This is a tensor with a mu index and a nu index. If you take a tensor and you combine it with a vector, you get a vector. This equation is a tensor equation in the sense because it transforms. Right? So, because we took care from the beginning to make sure that the equations of motion were Lorentz invariant, and we did that by making sure that the action was a scalar. This is the logic. Here's the logic. It pervades everything in field theory and particle physics in modern physics. Make sure that your Lagrangian respects the symmetries of the problem. If the symmetry of the problem is Lorentz symmetry, make sure your Lagrangian is Lorentz invariant. Once you do that, you don't have to worry, again, about whether the theory is invariant with respect to Lorentz transformations. In other words, you don't have to worry about whether it looks the same in every reference frame. Okay? Once you know that the laws of physics are Lorentz invariant and that the first 3 components of a certain 4-vector are equal to the first 3 components of some other 4-vector, then you know automatically that the 4th components will also match. The only way a system of equations can be Lorentz invariant if the first three components are 0, let's say, is for the fourth component also to be 0. So one can automatically conclude from the fact that we built a Lorentz invariant theory that the fourth equation must be true if the other three equations are true. They'll just form a complex of equations which include all four components. And another way to say it is if you took the equations for the first three components and then transformed them, you would simply pick up the fourth equation that way. But you don't need to do that. All you need to do is say, I know my theory is Lorentz invariant, and therefore, if the first three components of a vector equation are true, so must be the fourth component.
Question.
Yeah.
I follow exactly what you're saying in terms of the notation and how it was constructed and what it denotes
Right.
in terms of the symmetry and the
Yes.
tension. No, that's fine. That's great.
That's all there is.
But putting blinders on,
Yep.
forgetting all of the other things that we know,
Mhm.
we were just doing this derivation. We could add in the fourth equation, know that it was valid, but how would we know that it was meaningful in a physical sense?
I'll tell you what it is. It's energy conservation. Well, okay, it's sort of energy conservation. The first three equations, they're not energy conservation. I'll tell you what they are, though. The first three equations are of the form dp dt is equal to force. You know, dp dt is ma, right? I mean, p is mv and dp dt is ma. So they're roughly speaking, no, not roughly speaking, they're exactly the equations that the time derivative of the momentum is equal to the force, the first three equations. And the force being everything that's on the right-hand side of the equations. The fourth, and they tell you not momentum conservation, but they tell you how the change of momentum with time is responds to the existence of a force. The fourth equation tells you how the kinetic energy changes with time. Okay, how the kinetic energy changes with time. How does the kinetic energy change with time? The kinetic energy by dt, let's call it K by dt. Well, that's called work, right? And work is force times velocity. That's what the fourth equation is. The fourth equation is the equation that tells you that the energy changes in a way which is consistent with the amount of work being done. And that's not too surprising that, remember, that the momentum and the kinetic energy form a four-vector. Okay? So it's not surprising that, that the four-component equations are related, if not to energy and momentum conservation, at least to the way in which energy and momentum change in response to the existence of a force. So that's what the fourth equation is. It's the energy balance. It tells you how the kinetic energy changes when you do work on the system, and the work being done by the field. That's what this is about. But the sort of exciting thing is that you can represent the equations in this very neat Lorentz invariant form, tensor form, where the left-hand side is a tensor, namely a four-vector, and the right-hand side is the product of a tensor with two indices times a four-vector again. We contract the indices, and the contraction of the indices produces a four-vector on the left-hand side, matching a four-vector on the right-hand side. That's the exciting thing about this, that we used symmetry from the beginning. That told us the kind of Lagrangians we could write down that would manifest the symmetry. And then we plowed through it and discovered, in fact, that the equations of motion really do reflect the symmetry of the problem, the symmetry being Lorentz invariance. Now, there is another symmetry. The other symmetry is called gauge invariance, and we haven't gotten to it yet. We'll get to it next time. But, and I'll tell you what it is next time, but let me say that the three really fundamental principles that come time and time again, which we'll see in this simple example. 3 principles. The first principle is called locality. What locality says is that the way a thing changes only depends on what's going on nearby the thing that you're thinking about. A field over here doesn't change due to a field over there having some value. It changes because the field nearby has some value. The motion of a particle only depends on the values of the fields nearby. It also doesn't depend on the values of the fields at a later time or an earlier time. The equations of motion are equations between things at a nearby, in a small vicinity of the time, being related to other things in the same small vicinity of time, and space. How do we represent, how do we implement that? We implement that, that's called locality. We implement that by making the action should be an integral over all space and time, dx dt, of some kind of Lagrange density which only depends on the values of things at a particular point in the neighborhood, let's call it x and t, and, well, sorry, depends on things and derivatives. Let's say fields and their derivatives. In other words, it depends on data which has to do with local nearby concepts. And you add up the action in point by point by point in space, and what comes out is differential equations. Differential equations are equations which relate how things change from one point to another to neighboring things. You could imagine the action not having this form. You could imagine the action has in it things which involve products of fields over here and products of fields far away. But then your equations, when you worked out the Euler-Lagrange equations, they would have the form that the way things change over here depends on what's going on over here. No, that's not the way the action principle works. The action depends on fields and neighboring fields. Neighboring fields now means derivatives. So the way the field changes at one point is only determined by the value of the field at that point and neighboring points.
So that phi sub u is 4 components derivative?
Yes, 4 components. 4 components. Phi sub mu represents the 4 derivatives of phi. And as I said, it says that fields change in a way which depends only on what's going on nearby in space and time. That's the principle of locality, and it's no more or no less than saying that the action is an integral. Yeah.
How do you quantify nearby?
Well, by making derivatives, by saying it depends on fields and their first derivatives. That's all. Yeah. Fields and their first derivatives. Now, you could try putting in second derivatives, and there's an interesting subject there, but let's not get into it too much. Action principle, together with the idea that the action is built up out of incremental pieces, each of which depends only on a field in a neighborhood and its local neighbors.
What we've been doing here just depends on x and dx, right?
Yeah, when we're talking about the particle, yes. When we're talking about the particle motion, then we can substitute the statement that the Lagrangian along the world line of a particle only depends on the positions of the particles and neighboring positions along the world line. But also, it depends on the values of the fields at the position of the particle. The acceleration of a particle over here does not depend on the value of the field over here. It depends on the values of the fields in the neighboring region. That's the principle of locality, that the response of either fields or particles depends only on what's going on infinitesimally close by. Right. Second, Lorentz invariance. Lorentz invariance. In both cases, for both the particle and the field, the rule is build the Lagrangian out of scalars. Build the Lagrangian, make sure that the Lagrangian itself is a scalar. That's another way of saying that we'll all agree about the action within a certain volume of space and time. Lorentz invariance, L equals scalar. Those two principles are very pervasive. There is one more principle, which we haven't worked out yet. I have it in my notes, and so I'll write it down, but it's going to be the subject of next week. Gauge invariance. And that means, we'll find out next week. These three principles are extremely pervasive. Every theory that we know about, whether it's general relativity, quantum electrodynamics, the standard model of particle physics, Yang-Mills theory, all conform to these three principles. And basically, I would say anything else on top of that that you need is sort of incidental, and incidental not in the sense that it's not important, but incidental in this, what's the right word? That it varies from example to example in ways that don't really have to do with such deep principles. The fact, for example, that the standard model has 3 species of quarks, well, that's not contained in here. That's a sort of random addition, but the basic deep principles are these. So next time we'll learn what gauge invariance is. As I said, I advise you to go through these equations and figure out where the various things came from, because I certainly don't expect that you got it all in one sitting.
For more, please visit us at stanford.edu.